All right. So far we talked about BFS for shortest distance, and we basically were saying that whenever we are asked to find shortest distance from given source, and that can be shortest distance for a given target or multiple targets, we use BFS. Now we are moving on to the next step. When basically if the distance, though we are saying shortest distance, but if there is an extra cost, from going from A to B, if there is an extra cost, and that is where normal BFS will not work. So we have to use BFS with priority queue, and that is what ultimately Dijkstra algorithm is. Now let's check this in detail, what exactly we are talking about here. So if we are, let me switch to the graph. Let's suppose we are having a graph like this. Now, if we would have asked to do, get the shortest distance from A to every other node in this graph, we would have used BFS, and that would have given us that from A to A, this is 0 distance by default, right? From A to C, distance will be 1, 0 plus 1. Within 1 unit, you reached C. Same for A to D, because D is a direct path, then we will have 1 here as well. Same goes for B. In case of E, it would have been 2, because you need another node in between, right? That would have been our answer with simple BFS, breadth first search. Now what changed in this one, that there is an extra thing got included with it, that the edge which you will use to travel is having an extra cost with it. Means if you are going from A to C directly, you have to pay this 10. This 10 can be time, money, whatever. But basically your edge is having a weight included with it. Whenever there is an edge included with it, we don't have to reinvent the wheel. There is a known algorithm to do it, which is called Dijkstra algorithm. And that Dijkstra algorithm is actually very straightforward. Same our breadth first search. It's just that in breadth first search, if you remember the algorithm, in breadth first search, we were pushing all the nodes in a queue, and we were popping everything from the queue one by one. Like firstly, we would have added A to the queue, and then in our loop, all the neighbors to A will be pushed into the queue again, and A will be popped out, and that is how we will get shortest distance. Here in place of queue, we will just simply replace it with priority queue, or we call it heap, min heap as well, right? What exactly happening when we will do something like that? So in place of queue, let's suppose we are having a priority queue now. So what will happen? We will push A with 0 cost into the queue. So queue cost is something on which we will say we are doing this heap, ranking inside my heap. Okay, so that means whatever is minimum, it will come out. Now, because there is only one element in the starting, which is your source, when we are exploring the nodes in our BFS algorithm, it will come out, and we will try to insert all the neighbors of it. So we have one neighbor D, another neighbor B, and another neighbor C. In starting, because we don't know how much, what is the shortest distance and what is the cost required. So we can imagine that if nothing calculated, that means we don't know, this is infinite cost, right? So that is how we can do in coding, that we will assume this is infinite. In that case, now we will try to push D into the queue. D will be added with whatever was the cost of my node whichever is pushing the neighbor, plus the weight of the edge. So D will be reached in 4 cost. Then B will be reached so far in 6 cost, which is edge weight, and same way C will be reached in 10 cost. And ultimately in priority queue, because it will be sorted by the value of this cost, so this is how it will be popped out. So what is happening is, in my queue we would have explored all of these in this sequence only, but here, because this is a priority queue, it will be explored that particular vertex which is having the least cost next. So D will be popped out. Now when you are popping out D, you will see what are the neighbors to D. So to D you can go to, first you can go to B. So B right now the cost is actually, we calculated so far is 6, so it updated to 6 from infinity. Same, D was 4 and C was 10. Now B is 6 so far and D so far is 4. So 4 plus 1 is 5. We are actually bettering that. This will be a better distance. So we will not hesitate pushing that B in our queue again with 5 as the new cost. And whenever you are doing it, whenever you are pushing it into priority queue, because this will be sorted, so this will actually come before this B. It will not delete it, but here it will be inserted. If you know priority queue, right? Basically nothing but a sorted order you can imagine this data structure will give you. So D will push B first with updated value. Then D is having another neighbor E, which is having infinite so far. So we will have E with 4 plus 2 as 6 value. So E will be pushed with 6 value, and that will again in sorted order, B5 will come first, then B6 and then E6. You can say it like that. So D is done, and that is whenever you popping out, that means that was the best value. Now we will explore, this is my best vertex next, which is B5. So we are not exploring C in order which we inserted it, but we are exploring in order whichever is the best next vertex can be, right? Now B will come out, and B first neighbor is A, but A is already 0. You cannot better that. So hence this will not be pushed. Then B is having C as another neighbor. B's value is 5 so far, the best value, 5 so far. And to reach to C, we will need 5 plus 3, 8. So C will be updated to 8, and we will again insert C into this priority queue with C comma 8. And as reordering will happen, C8 will come first. Let's continue exploring. B, another neighbor is E with 6 as distance. And because B is already 5 and this edge we are having 5 here, so it will be 10. So we will not push E again into our priority queue. All the neighbors of B are done. The next from the queue will come out as E6. E6, so B5 is done. You can say if B is already done, then we don't need to, when we are exploring it again, if it is already added to the answer set, we don't need to explore it again. Hence we will simply pop out B6, but we will not do anything, any processing with it. And we will see one single line will help us doing that. Then next E6 will come out, because that is the best node we are having. E6 again will not better. In fact, E6 plus 1, so C will be updated to 7. So C7 is another value will be pushed in our priority queue, and that's it. E will not update any other node, so E6 will come out. Now C7 will come out and add it to our answer value. Then C8 will come out, but it will not update anything. C10 will come out, but it will not update anything because C is already added to our answer set. So this is how Dijkstra will be achieved. So this is a known algorithm. We are not basically trying to do any algorithm here. We are just trying to see what it does, right? So we will simply change our BFS algorithm and we'll see what minor changes we will do in that to have our Dijkstra algorithm ready. In fact, let me get that Dijkstra code here. All right, let's check this code. So if you remember what we were doing in our breadth first search, we were pushing everything into our queue. Firstly, we were adding our start into a priority queue in our queue, right? So here we are just adding it into a priority queue where 0 is obviously the cost to reach to source from the source. So start at 0 cost we can reach easily. So that is what we added here. Then we were popping everything from our queue. Here we were running a loop on queue. Here we are running the loop on priority queue. Then we were popping the first value from the front of the queue. Same thing we are doing here. It will give us the node, and because here we are having a cost which is extra thing, so we are getting the node and cost. This line is similar to what we were this is actually an extra line, so let's talk about it a little later. In our breadth first search, next thing we were doing is we were pushing all unvisited neighbors of this particular node U. So here also we will get for U what are the neighbors I am having with edge weight of the edge, right? Now there we were checking if this is not visited, simply add it into the queue. Here what we are doing, if the distance so far, whatever is the distance to reach to V is, can I improve it? So can there be a better distance? So that is what we are doing. Whatever is the current distance of, current node plus the edge of the weight. If this is giving me a better answer than existing answer to reach to that V, in this example, like we did earlier, first we were able to reach to C in 10 cost. And then later from E to C, we were able to reach in 7. So that is what we are saying here. We can push it again into our heap. And then we are updating the distance. That's it. So there is no visited array, but this is how we are checking whether we need to push it again. If there is a better answer to reach to that node, we are simply pushing it. If there is no better answer, we are not pushing it. Now coming back to this line, which I talked about, that if current distance means I am maintaining a distance array, so all the value which I was saying here that C is having 10 and then C is having 8 and C is having C. So this 10, 8 and 7 against C, that assume I'm storing in this dist array. So distance to this particular value, if that whatever current distance is coming now, which I was talking about, that once I explored my C7, so C7 is kind of came out from my priority queue, then C value is already updated to dist at C is already updated to 7. When C8 will come out, then I will not even continue in this code. Because of this line, we'll simply check if current distance, which is obviously 8, is greater than whatever is the distance already updated in my finally, in that array, then I don't need to do anything, just continue. So that is how I will not explore that same node again. So I may push it more than once, but I will not work when I will pop that value. So yeah, this is actually a very important optimization, and this will help in time complexity, worst case time complexity, and we'll calculate that time complexity. But this is overall is the Dijkstra algorithm code which we will be able to use to compute shortest distance when a weight is given. And obviously we have our table ready that where we cannot use it even if weight is given, for example negative and all. So we'll talk about that, but takeaway from this one is that this is the algorithm which we are going to apply, and we'll practice some question on it. Though we saw the code of Dijkstra, but there is one important thing which we should do. We should establish what exactly is the difference between Dijkstra and BFS, and we should go deeper into it a little bit, because it's not possible that we will remember the algorithm, but once we understand it, then it will be easy to have in subconscious mind. So if we would have used breadth first search, why it will not work when there is a weight on the edge? So let's just try to debug it, go over the graph a little bit, and then maybe we'll be able to establish the difference. So my source is A. If I am going with breadth first search, I'll explore all my neighbors. So first C, then next neighbor is B, then next neighbor is D. So these are the three neighbors. And because cost is involved, if I'm doing it with breadth first search, obviously I will have that cost also in the queue. So 10 will be the cost, because that is the edge weight or cost which we have to pay if we are going via this route. Same for B, it will be 2, and for D it will be 4. If we go with the Dijkstra, nothing changes here. For A, source to source is obviously 0. So same, C, B and D, we will push these into priority queue, and cost will be 10, 2 and 4. This is where things will change now. In case of breadth first search, next we will pop out C, because this is next into the queue, and hence we'll explore the neighbors of it. And C is already traveled, so we already kind of closed this here. Next, C do not have any neighbor to go from C here, so we'll not do anything. In case of B, we have C, but C is already, you can say, is already visited, hence we will not explore this again. And if we write that condition here, that if cost is greater than this, then we'll see that we will go into an infinite path eventually, and we will never be able to conclude our graph. So here what is happening is, because I'm not exploring C, that means I already concluded C with 10 as the cost, which is not the optimized cost. If I would have explored it after B, then obviously the cost will be 2, plus from B to C this is 3. So C would have had cost of 5. Okay, so that is where breadth first search will not work when edge is there, edge is weighted in a graph. In this case, in case of Dijkstra, we are actually now, because this is a priority queue, this is a min heap. So what we will get from the heap is, or this priority queue is B, because this is having the least cost. A is already popped out, that is why we pushed all the neighbors, right? Now when B will pop out, so what we will do is, what are the neighbors B is having? So B is having a neighbor which is C. Now C in this case, what we do in Dijkstra, like we saw in this code, right? If we can improve the weight, we will improve, means the cost, we will improve the cost. So from B to C, will be updated again, added into our queue again with 2 plus 3, 5 as the new cost. This is still into the queue, but it will never come out. Okay, so now we pushed this one. Now from B, do we have anything else to travel? A, but A is already having a 0, so that we can ignore. And E, so E we will explore. We will add it into the priority queue with how much cost? For B it was 2, and then E is, it will be 7. So this is pushed into priority queue now. Next, which will come out of this priority queue will be D4. Okay, so D4 coming out of the queue, and what are the neighbors we are having to D? So for D we are having B, but B is already, now we can say, is concluded. It is visited already because we popped it out from the queue. If this is popped out from the queue, as per our algorithm, if we go back, which will happen here only, that our current distance is greater than whatever is the distance of the U which will come now, which should be the case because min heap we did, and negative is not allowed in Dijkstra. There's no negative weightage, so it's not possible that once you popped out something, there can be a better distance to it later, right? That is why priority queue or min heap is there. So B will not be getting pushed again. Then from D, next we are having is E with 4 plus 2, 6. So E we are adding again with an improved cost of 6. So you will see now D will say is kind of done, because C it will not push again as C is already having a 5. So we don't need to update again. Next thing which will come out of it is something with the minimum value, which is C in this case, right? So this is how we are expanding. So now you see the difference, that we are expanding on the vertex which is having the minimum cost in case of Dijkstra. On other side, in breadth first search, we are expanding the next node in the queue, right? Difference is obvious, that one is using priority queue and other is using queue. That is why it is happening. But to remember it, in an interview, it will not be that easy, right? All right, so let's move forward. All right, let's do our first question with Dijkstra. So what exactly is given in this question is that we are having, you can say, networks, right? That you can imagine that this is node 1 to node 2, and it is given like how much time it takes for a signal to travel via that edge which is connecting those two network towers. Okay, and you are also given a K node which is the source, and we need to calculate how much time it will take if we are sending a signal from K, how much minimum time it takes to reach that signal to all the connected towers. And if it is impossible, means if there is one tower which is, you can say, disconnected, or by somehow you will not be able to reach to that one, in that case return -1. This is an edge case, we'll leave for now. Why this is, so this also we could have thought of doing it via breadth first search, right? If we do not, right now we know the context that we are studying Dijkstra, but because this is also talking about minimum cost, shortest distance from K to all other, BFS looks to be a candidate, right? If 2 is my, you can say, source, which is K in this graph I'm talking about, then from K to 1 and K to 3, these are my next neighbors. Here I can reach, you can say, is whatever given time. So cost to reach to 1 will be 1, cost to reach to 3 will be 1. And then next we will explore this. We cannot go anywhere from 1, so it's okay. From 3 we can go to 4 in 1, so 1 plus 1 it will be 2. Hence 2 will be my answer, that in 2 times, ultimately this much time it took to cover everything, right? That works again same if edges are all are 1, means same cost, or if there is no weightage, means it's like in no time it reaches from one to another, then how much time actually it took to reach to all the towers. Means if it doesn't take any time to reach from one to the neighbor, or you can say 1 unit it takes, then it would have been done by breadth first search. But because the weightage is different, that from 2 to 3 it might take 1, from 3 to 4 it might take, the edge weight is different, right? In that case we have to use Dijkstra, like we discussed in the last part. So let's just continue with our the code which we learned about this kind of question. So this is a direct application of Dijkstra. Okay, so the code we had for this, I'll get the code directly. So we were saying, if we are having a graph, if we are given a graph, so I'll call it Dijkstra. So I'm saying self send me a graph, start node and a graph, and I'll be able to run this Dijkstra algorithm, and I'll be able to return the distance, which is that to whichever node how much time it took, the minimum time to that. Now first thing first, we are given a graph with this kind of an array. What do we call it is adjacency matrix, right, with weightage. So I'll try to because how we are reading the graph here is okay. So how we are expecting is that we will have it like an adjacency list. Okay, so we'll try we'll first convert it into adjacency list. So that can be like graph is equals to def default dictionary of list. Now what I'm going to do is, for every time which is having three things, u, which is my source, to destination, in how much time we will reach, in my times adjacency matrix given. So what I'll simply do is, for graph at u, I will append in my list. What I'm going to append is an array which is having v comma w, because that is what I'm getting from my graph in line number 17. All right, now after running this, my graph will be ready. And this is directed one, so u, v and w is we want, not the other. We don't need to add both ways. Now what's next? If I pass this graph with k to my Dijkstra, this one, I think that should give me the answer. already, because what it will do is first it will push the start with 0 into priority queue. Then it will kind of pop out one with the minimum cost, and it will check if we can improve or not, mostly, and then it will push all the neighbors where we can improve the cost. Yeah, so one thing which is okay, so dist is already made up here, so we don't need to worry about it. By default it will be infinity, so ultimately, so yeah, so next thing is I'll say dist will be the output of my self dot Dijkstra method, where I'm passing k as my start and graph graph as another input. From this one I should get the maximum one out. So I'll say answer is equals to max from my dist array, right? The only check I need to do is if I'm unable to reach to anyone, so I will say if the answer equals to this by any chance, that means I failed to reach to any node. Otherwise I should just return the whatever is the maximum value I got in that dist array. Let me just, this looks fine to me. Let me just check if any compilation error is there. It is, oh, in indentation. So okay, yeah, this is part of the class, so I should add a tab. Anything else? Nope. Let's see. Okay, it is complaining about index is out of the range because I'm having this 0 to n and this guy is having it 1 to n. So I'll do it like this way. Now if that's the case, the only thing I need to do is, once I'm getting this, so answer at 0th will be 0 by default. This I'm doing because we are having 1 to n, so whatever is at 0th index is useless to me. It is complaining about one more thing, still out of the index. All right, so I converted it into my adjacency list. I can actually pass n explicitly. So this is my graph and this is the n, and that I can get here. So I don't need to calculate the n. Oh yeah, so I need to put and dist 0 a 0 value. Cool. Yeah, that was just the typo I was doing. Let me just submit it. Perfect. Yeah, so this was a direct application of Dijkstra algorithm. We were able to run it. Now let's talk about the complexity analysis of this one. So let's try to compute the time complexity of Dijkstra. This is a little bit of, again, not direct, means it's not like just by seeing the code. It's not easy to compute this time complexity. Yeah, so though it's very similar how we computed for breadth first search, right? That you should be knowing how you are pushing into the queue and how you are, kind of expanding, relaxing over edges. Okay, let's just try to establish that understanding. So what exactly is happening? First thing first is this for loop, right? Like we did in breadth first search, it's very similar to that. How many times this for loop will run overall, we have to see explicitly. So this overall will run for all the edges in my graph. As simple as that. No matter what the loop is here, while loop, it's not like for every iteration of while loop you will run it for all the edges. Even in worst case scenario, all the edges in my graph will be kind of processed by this for loop. So every edge will be processed only once. So that is why I can very safely say, so total number of time this for loop will run is equals to the number of edges. As simple as that. It's just that line number 19, what is happening here is we are pushing it into a priority queue. This is not a queue. So pushing anything into the queue is order of 1. That is why we were not worried about what we are writing inside the loop in breadth first search. But here this is priority queue. So push in a queue or in a min heap is actually log of whatever is number of items will be there in worst case. So what can be the worst case size of my queue here or priority queue here is all the vertexes can be there. So we can say log v it will take to push an element into my priority queue. Hence, this for loop overall will be e log v. Okay. Now going to my while loop. My while loop overall will run on all the elements in my priority queue. And like we just said, this will have worst case scenario all my vertexes. So it is safe to say that my while loop is v, right? Basically number of vertexes plus same line number 10. Here we are pushing into priority queue, hence pushing, pop from the priority queue, right? So that also in min heap, though we can get it from the top directly. So are we also pushing anything into this one? No. So pop, yeah. So pop from the min heap is same as push. It takes log v because whatever adjustment happen, you remove head, but then you have to replace it. So overall operations take log v, log of whatever number of elements are there. So worst case scenario, it will be v. So v log v. Though these loops are, for loop is inside the while loop, so it should have been the multiplication of these two, but that's not the case. Like I said, this was the overall how many number of time this will run, right? So there is an addition. That's why there is an addition between these two. So it is when you will do the plus, so we will take common out. So it will, you can say safely say v plus e multiplication with log v. That is big O of time complexity of my Dijkstra algorithm. Very similar to what we did in breadth first search. Why we are doing an addition here in place of multiplication? Because first we computed the total number of time it will run, and then we just did the addition of these two. Space complexity should be straightforward. We are using a priority queue. That means all the nodes, number of vertices will be there. So order of V. And then other than this, we are using this distance, which is again same. All the vertices will be there in this one. Other than this, nothing else we are using, outside my graph. So hence you can say order of V is overall space complexity I'm using in my Dijkstra algorithm as well. So yeah, this is the analysis of this algorithm, which is Dijkstra plus for this network delay, how much we are doing. That's it for this one. Thank you very much. Let's continue to the next section.